Hello everyone, this is Professor Felipe Rodriguez. I'm recording this video because one of my students had a question about assembly line balancing. So I figured I'm going to use one example from the Jacobs textbook, chapter 8, if I'm not mistaken, example 8.2, in which we're going to handle the assembly line balancing with a more complex assembly line. So let's move on. Um, As usual, this is MOS 3330, Operations Management. The unit is Process Improvement, and this is an example of assembly line balancing. I'm Professor Felipe Rodriguez from the School of Management of Economics and Mathematics from King's University College here at Western University, Canada. So process improvement, as I've shown before, two basic readings for this part. One is chapter 4 from Cashon's textbook. Again, I recommend this book a great deal. It's very process oriented, very good for decision making, especially in a program of operations management. That will be an introduction or a core operations management course within a business or a management degree. And then also chapter 8 from Cashon, which is really good. In chapter 8, not only you have assembly line, but you also have layout and several other topics that would be interesting if you want to go further into process improvement and facility layout planning. So let me move. I think I'm going to have to minimize this a little bit more. So the learning objective that we have right now is to balance a process. By reallocating work from one step to another, we're also going to calculate a series of efficiency measures. So let's move on. Always remember, there are a few things that when we're dealing with operations management, we have to keep in mind. The very first one is about operations is about matching supply and demand and sustainably, okay? People, planet, and profits. Also, operations must be aligned with your strategy. So cost, leadership, and differentiation require completely different kinds of operations. So you have to be aware of that. You cannot manage what you can't measure. So every process in your operations must be followed with some kind of key performance metric or indicators so you can evaluate and make decisions, right? So if, cause, then, effect. So if you can measure your assembly line, the key performance indicators in your operations or in your process of any kind, you can therefore predict, hypothesize changes, and observe changes in behavior and make better decisions, informed decisions. The process triangle, inventory capacity and variability, this comes from Little's law, where the size of a system equals to its arrival rate times the time in the system. Or if you want to think about this in terms of an operations perspective, inventory is always the flow rate times the flow time. And if you have some kind of misfit or misalignment of some sort, inventory builds up, it creates waste, capacity becomes unbalanced. Therefore, you're going to have lots of idle time, or you're going to have a really high utilization rate that won't be able to absorb variations in demand, and variability will be excessive. Therefore, it will be hard to establish a flow into a process. And we've already seen a little bit of that with respect to takt versus cycle time. And remember, continuous improvement. Every time you're looking into a process, you got to think there's got to be a better way. How do we add value, or how do we subtract time that is non-value added? So any kind of cycle, like a PDCA cycle or a DMake cycle, continuous improvement. There's always a better way. And also, operations has a deep connection to marketing, where you're matching supply and demand, but also with finance. And remember, in a statement of earnings, your top line is is your demand, which for us implies our flow rate, right? The arrival rate into a process. COGS, cost of goods sold or cost of services, depends on how you see things, is the sum up of your inventory plus any kind of overhead that you have from your manufacturing, which is your process technology and direct manufacturing costs, labor costs, right? So COGS is basically inventory and flow time. So look at that. We're basically talking about Little's law in the form of finance. So the better off you are by reducing your flow time or by improving your cycle time, you have less inventory to worry about, right? And you therefore you have a higher gross margin. So measures of process efficiency. Let's think about this for a moment, where, as I was saying from the previous chapter, we got to think in terms of labor content. The labor content is the sum of all your processing times for each one of your the units inside your process. So if you can sum up all the individual tasks, each and every one of them, you put them in a list and you see how long each one of those takes, sum these up, and you know what that time in seconds is. That's the labor content in your process. While on the other hand, the average labor utilization is a different kind of efficiency. We can think of that in terms of a overall efficiency, right? Where you're dividing the labor content that you just found out right now. You divide that by the number of workstations or the number of steps or stations that you have in a process times your measurement of demand or the rhythm or the beat of your demand that we call takt time, right? So remember about this. The more workstations you have, as you increase the size, the number of workstations, you're dividing these things by a bigger number, right? What happens to your takt time? The more demand you have, you're going to be needing to balance that with your number of workstations, right? So a small takt time, if this is really small, you got to balance those things out to achieve a high efficiency, okay? So let's move on. So what is takt time? Is a measure driven by demand, your available production time, divided by your demand. So we've seen this before. So this is my total production time. All right, so for example, in a shift, I have 8 hours. That's what your total production time is, and the required quantity, that's your demand. So that's how you figure out your takt time. This is the beat. This is the pace in which your assembly line should follow. Okay, so it's driven by demand. We're looking outwards, and we are going to think of our process, how we can match the external demand with our internal capacity, right? So takt time is 1 divided by demand, which is great, while cycle time is 1 divided by your flow rate, right? And your flow rate is a measurement of your process capacity. Those two things, this is external. You're looking outwards, right? This is demand. Cycle time should be about supply. So let's think about how to choose the staffing level to meet our demand. We will need to talk about target power. And target power, or other operations books call these the theoretical minimum. They call it NT. So I'm going to put this down here, theoretical minimum number of workstations or work centers, whatever you want to call these, or stages or steps in your process. This will be your labor content, which is the sum of your processing times divided by your takt time that you already know by now. This is 1 over your demand. Sorry, this has to do with your demand. Ooh, let me erase this a little bit. Just a second. Apologize. Just a moment. Okay. So, sorry. Go back. So this has to do with your demand, right? This follows your demand. So let's think about this a little bit. So how do we balance our assembly line? So first and foremost, you got to find each task required to finish your product or your service, right? So specify the sequential relationships among those tasks. Which one has to follow which, okay? Sometimes they work in tandem. So you have one task following to another one, that then goes to another one. But you know what? Sometimes you have parallel tasks, right? And this one follows to this one, and then this one, they link up. So you got to figure out the sequential relationships among each one of the tasks. Then you determine the labor content. That's the sum of your processing times. Determine your tech time uh, by dividing the available production time divided by your demand. Now notice this, that the production time is seconds per day and demand is units per day. So one thing, days, they're going to cancel. You will end up tech time in seconds per unit. That's the beat of your demand. On average, always remembering about this, on average, every so many seconds, one new customer will arrive, one new order will arrive, one new delivery must be made, okay? One more patient will come, or one more call will come into your call center, one more order will come into your system or your website, whatever. Then you determine the target manpower, and the target manpower is measured in terms of workstations or work centers or employees, whatever you want to call this, right? So the labor content that we calculated from before, this guy over here, and the tech time that we've just calculated. Now remember, labor content is seconds per unit. Tech time is also seconds per unit. So these two things are going to cancel out. So the measurement that you have is an absolute, is a number without an indicator, okay? So you will end up, for example, with 10 workstations, with 11.2 workstations, whatever. That will be your target manpower. And you should always round that up. So you have integer numbers. Okay, that's a key. The integer number that you find as you round up will be the number of steps that you will require to have in your process. Then you need to select a primary and a secondary assignment rule. So basically, how is it that you um, place and you design those tasks into each one of the workstations? So usually what we do is the largest number of following tasks. That's the one task that you pick first to place in a workstation. And the tiebreaker usually is the longest task time. So you want to make sure that the long task times are as early into the process as you can make them so. Then that is a measurement that will enable you to have a little bit less of idle time. So you assign those tasks into the workstation, and you keep doing that to each one of the workstations. So this is an algorithm, right, in which you repeat those steps. And then you evaluate the efficiency. So that could be, like I said before, OE. Sometimes we can measure this in terms of OEE, overall equipment efficiency, or another way of seeing this is the average labor utilization. So we already know the labor content from above. So you can link that guy over here. And then the number of workstations you calculate it from your target manpower and your tech time. You also calculated from before. So you find a number that represents a percentage value. For example, 85% utilization rate. As an example, that means only 15% of your time is actually idle. Everything else is a value-added time. And then you should rebalance if you think that things are kind of off or don't make a lot of sense. So let's look at this example from the Jacobs textbook. This is the example 8.2. I have these number of tasks going from A all the way to K. This is the amount of seconds each one takes. And I know that in order for me to execute task B, I need task A to be executed first. So you can draw this process. You start with task A, you know it takes 45 times, right? Seconds. And then immediately next will be task B. And you keep task B. And you keep doing that until you find a task flow, just a little bit like this. So task B is preceded by task A. Then you have task C, that's 9 seconds, and you need B to be done. So B now goes into task C. Those are the 9 seconds that you need. Task D has no precedence, so you start a new flow. So this is something new that we haven't done it yet in our module, in our course. So as you move down into task E, task E is 15 seconds and requires D to be ready. So there you go. Now you're going to D. So task F, 12 seconds and requires task C to be performed. So this is where F is going to go, right? Task G, also 12 seconds and also requires C. So you're going to move it this way. And let's look at H. H, 12 seconds and requires E. So now you can see there's basically two parallel process flows, task flows happening right now. Task I requires 12 seconds and then it goes into E. And then task J requires all these four. So they're going to link up into J right there. Only 8 seconds, and then after task J, we have task K requiring 10 seconds, and then the process is done. Excellent. So now I know how my process, how the tasks look like. This is not necessarily a process just yet, because as we have right here, each one of these could be a single workstation, but we should see if they in fact should be a single workstation. And how is it that we do that? We observe what is the need from my customer. So what is my demand? In this particular case, my demand is 500 units per day, right? And I have 8 hours in a shift, in a daily shift with 1 hour setup. So my available production time is actually 7 hours. So let's think about this for a moment. Just by looking to this process, we can tell that if each one of these activities were a single workstation, there would be a bottleneck quite clearly. And that bottleneck might be task D. That's the longest task. So when you're over here at task J, waiting for parts to come through, you will know that from from this task flow over here, you're gonna have 1 unit every 45 seconds. That's the beat of that upper flow. And then the second one is 50. So every 50 seconds, J will be able to assemble those two separate units. I'm actually going to use a different color. Let me do like this. So this is one subassembly. This is another subassembly. And then J is going to link those two up, right? So this on average will be every 50 seconds, and this on average every 45 seconds. So in short, it would take, you can only link up these two things every 50 seconds, then another 8 seconds, and 9. There you go. So we're working at a 50-second interval of time over here. Is this enough to fulfill my demand? or can I do something else? That's exactly how we're going to assemble um, our line and balance that. So I already specified and put into sequence the relationships among those tasks. Now I'm going to determine my labor content. So let's do this. How do I determine my labor content? I can look at all these tasks, and if I sum them up, the sum of that is 195 seconds. So there you go. So the sum of processing times, this is 195 seconds per unit. Okay. Now let's determine our takt time. So the takt time is the available production time in seconds per day. Do I know this number? Well, if I look back, I know I have 7 hours. So what can we do with 7 hours? Okay, so it's 7 hours. 7 hours is actually, if we make that into seconds, that's 420 minutes times 60 seconds, which is 25,200 seconds. Okay, so this is my numerator right there. And my demand is in terms of units per day. So this is 25. Let me erase this a little bit, make it a little bit better. So those 7 hours, I'm using green. So 7 hours, so that is actually 25,200. And I'm gonna, this is seconds per day. And my demand is 500 units. Oh my God, that 5 is awful. Sorry. All right. So this is 500 units per day. So observe that this per days are going to cancel. So in the end, what you have here in terms of your takt time is that, so I can divide that. So cut these two zeros, cut this guy. So 252 divided by 5. So I'm going to end up with 50.4 seconds per unit. This is my takt time, 50.4 seconds, okay? Now let's determine what is my target manpower. So remember that target manpower in terms of workstations, this is also what we call the theoretical minimum number of workstations, right? So the labor content is 195 seconds per unit, and my takt time is, oh geez, there goes the weird number again. Apologize. Let me erase this. And so 195 seconds per unit. And this guy, my takt time is 50.4 seconds per unit. So observe now that seconds and seconds, these things are going to cancel out each other out, right? So I can cancel this, I can cancel this. So 195 divided by 50. So what we get here is 3.87, give or take. So in the end, we have to round this up. So let me round this up. This is actually going to be 4. So I need 4 workstations. Okay, that is my theoretical minimum. So in an ideal world with no idle time, 4 workstations would be enough. Okay, so that's what my target is. Question is it really realistic? Are you going to be able to achieve that target? So now we can assign those tasks and evaluate the efficiency. So ideally, what we can do at this moment in time, we don't really know the correct number of tasks just yet, right? We know the theoretical number. So let's see how efficient theoretically we can be. Okay, so the labor content is 195 seconds. I'm going to divide that by the number of workstations. So this would be 4. So theoretically, I would have 4 times my tech time. That would be 50.4 seconds. Okay, so theoretically, what would that be? 195 divided by 50.4, and then divide that by 4. So theoretically, I could be 96.7% efficiency. Okay, that is what I'm aiming for. Let's see if we can make that, if we can be that efficient. Notice that we're not 100% efficient already, but we're pretty close. So let's see. Okay, so how do we move about doing this? We first select the task with the largest number of following tasks. So let me hide this little bar over here so it's not in our way. Is this what it is? Yes, excellent. Okay, so let's look at the tasks with the most number of followers, right? So if you look at A has 1, 2, 3, 4, 5, 6. If you look at D, 1, 2, 3, 4, 5. So I keep doing this, right? Number of followers for each one of these activities. So obviously, if my rule is find the one start with the one with the largest number of following tasks. That's how the algorithm works. So clearly that should be activity A. So I'm going to put here in this workstation number 1. Okay, and the task that we're going to workstation number 1 will be task A. All right, now how long does task A last? Well, it lasts 45 seconds. So let me put over here 45 seconds. So if my tech time, what was it that I calculated again? Is it 50.4? I think it's 50.4. So I should be running at 50.4 seconds, okay? So let's look at what the remaining assigned time is. So at 50.4, I already spent 45 seconds. So I'm going to write this down here. So 50.4 minus 45. Now, how much do I have left? I have 5.4 seconds left. Okay, so in theory, now I should be able to look if there are any tasks that can be added into this workstation. So I only have 5.4 seconds left. So I'm going to look into each one of these activities. Do I have anyone with 5.4? I don't have anything with 5.4. So can't do anything anymore. So workstation number 1, there's no feasible remaining tasks. So all of this is empty. Is that okay? So that's workstation number 1. Now activity task A just became workstation 1. All right. Now let's see. I'm going to change the color of my dude over here. So let's go to green. So let's go to workstation number 2. What can we do with workstation number 2? So now let's look. By the way, A is done. So I'm gonna cut A out. There you go. Okay. Now let's look at the next task with the highest number with the most number of followers. So what can I do? So B wouldn't quite work. Oh, let me look at my list over here. Well, now I have B, and I also have task D, okay? So these two tasks have the same number of followers. So how do I break this tie? Let's look into what I had before. I select the one with the longest task time. So the one with the longest task time is activity D, task D. So I'm gonna put task D right there. So how long does D take, the processing time? So the processing time, let me call this processing time P. So the processing time P over here is 50 seconds. So my takt time is 50.4. So now I have 0.4 seconds remaining. So there's obviously nothing that I can do. So task D is now workstation number 2. All right. So can't do anything, can't do anything, can't do anything. So right, I'm gonna cross D out. You're out, my friend. Gone. So let's see. Now, sorry. What's left? Well, let's look at the one with the highest number of followers. Now this seems to be B back again. So I'm gonna start workstation number 3, picking a different color. Okay, so workstation number 3. Excellent. So, and workstation number 3 starts with task B. Task B, this dude over here, is really, really short, very fast, 9 seconds only. So what am I going to do? 50.4 minus 9 seconds. So 50.4 minus 9. So what we get over here is how much? Oh, no, sorry. I apologize. No, it's not 9 seconds. It's 11. Sorry about this. Okay, let me erase this guy and this guy. So this is 11 seconds. Task B, it says right here, 11 seconds. So minus 11. So what we have left is 39.4. So 39.4 seconds. Right. Are there any? So I'm going to put you away, my friend. So B is gone. How many more tasks can I proceed right now? I still have 39.4 seconds remaining. So let's look at this. So from B, I can only go into C. So C could be a feasible remaining task. So C could work. Let's see what else could work. So C could work, and also D is done. So now E is empty, right? Oh, by the way, this is already done. So E, so I could only work with C or E, right? So this and this. Those are the only 2 tasks that I can follow. So C and E. So which one am I going to choose? So what's the tiebreaker? So the task with the most followers. So let's look at task C. Task C has 4 followers, and task E also has 4. Oops, what am I going to do now? Well, so C, the one with, so C and E are the ones with the most followers at this moment in time, but the one, so I'm going to tie break this, the one with the longest processing time. So C is 9 seconds and E is 15. So I'm going to select E. So the next task is E. So what do we know about E? E is 15 seconds. Okay, so I'm going to subtract those 39.4 minus 15. So what I have left right now is 24.4 seconds. Okay. And this guy is gone. Okay. All right. So let's look into the feasible remaining tasks. So we know C is good to go. A is already selected, right? So C is okay, H is okay, and I is also okay. So I'm going to put over here feasible remaining tasks, C, H, and I. So let's look at the ones. So C, H, and I. So which one of these have the most followers? C has 4 followers, H and I have 2. So this will be therefore task number C, task C. And that's the one I'm going to decide to do it right now. So here's C. So C requires 9 seconds. Okay. So I'm going to subtract 9 from those 24.4 seconds. So now I only have 15.4 seconds left. And a whole bunch of feasible tasks remain, right? So C is gone. So let's see, what can I can do F. F can be done. I can do G. I can also do H. And I can do I. All right. So which one of these have the most followers? So let's see. So this guy is done. So F, G, H, and I, all of them have 2 followers. So what am I going to do? Damn it. So let's look into processing time. So all of them. So this is all. What about longest processing time? 12 seconds, 12 seconds, 12 seconds, 12 seconds. Oh, that's no good. So they tie on everything. So you know what? I'm going to pick alphabetical order. I have to tie break this thing. So therefore, I'm going to pick task F. So how long does F take? 12 seconds. I'm going to cut this guy out so I never see this guy again. So now I've selected F. Okay. So F is 12 seconds. So 15.4 minus 12, there's only 3.4 seconds left of idle time. Looking at the remaining tasks, there are no tasks that are that short. Therefore, so now I'm going to stop this iteration right there. So B, E, C, and F, they compose now workstation number 3. So let me see if I can put all of these guys together. Am I doing it right? Yes. So this is workstation number 3. There you go. Now let's look into the next workstation. I'm going to change colors again. I'm going to make this guy, I don't know, sure, dark red. So station number 4. So what's going on with station number 4? G, H, and I. So G, H, and I. All these 3, and actually all these 3 can be done at this one moment in time. So how do I proceed? Well, let's look at the one with the most number of followers. G, H, I. They have 2 followers, and they all have processing times that are similar, right? G, H, and I. So what do I do right now? what would be my solution? So they all have to go. They all have 4. They are all number 4 in the processing time rank because they take 12 seconds. They have the same number of followers. Okay, so what is it that I can do at this moment in time? I selected F, so now I'm gonna pick one of these 3 to start my iteration, right? And I'm gonna select task G. So task G is 12 seconds. So we have to restart from 50.4 minus 12 seconds. I go to 38.4 seconds. What are the tasks that are feasible at this moment in time? I cannot perform J because H and I are not done. So the feasible tasks, so I pick G. Feasible tasks are H and I, right? The task with the most number of followers, they all have the same number of followers, and they all have the longest processing time, right? So I'm gonna pick in alphabetical order. There you go. I'm gonna select H. So, oh, by the way, G is done. Now H is also done. So let's go to, so H is 12 seconds, 38.4 seconds minus 12. That means 26.4 seconds. The feasible remaining task is I, right? I just picked H right there. So I cannot move to J because I is not ready. So now I have to pick I. So I becomes the next task in this workstation. So let's see what's gonna happen now. I is 12 seconds. I'm gonna cross you out. Don't need you anymore. So 26.4 minus 12. Now this remains therefore 14.4 seconds. Okay, so what can be done next? From I can perform J. I cannot perform K because only J is left. So the only alternative that I have right now is task J. All right. So how long does J take? 8 seconds. Excellent. So J takes 8. 14.4 minus 8, that's 6.4 seconds. How many more feasible tasks can I have? So I selected J, right? So the next feasible task is J out. J is out. Now here's K. So what's going on with K? K is 9 seconds. So I cannot fit 9 seconds in 6.4. So this is my 4th workstation. Workstation number 4. Excellent. So finally, now I'm gonna use black. Black is fine. So workstation number 5. Now remember, my theoretical minimum, my NT was 4 workstations. In fact, it was 3.8 something, right? I'm already over it. I'm gonna need 5 workstations. So let's go into K. The task time for K, the processing time for K is 9 seconds. And out of those 9 seconds, there will be 41.4 seconds of idle time. That's a lot of idle time, right? So, and that's it. There are no tasks left. So that is workstation number 5. So my process has 5 workstations. Now notice a few things. Workstation number 1 has a little bit of idle time. Workstation number 2, very little idle time. Workstation number 3, also a little bit. Workstation number 4, little bit, and workstation number 5, there's a lot of idle time right there. So from an intuition perspective, very intuitively, you should see that the workstation that has the least amount of idle time is the busiest, right? So that will tend to be your bottleneck. Let's see if we can confirm this, okay? So I'm gonna cross out K just to be consistent. So can we now calculate our efficiency? Let's calculate our efficiency. So what is our efficiency? The same 195 seconds that we had before. How many workstations are there? We have 5 workstations, and my cycle time, which is at this moment my tech time right now, is 50.4. So my efficiency, or my average labor utilization, is therefore around 77%. So let's compare that 77 with that 96.7%, and you can see that there's a lot of loss. There's a lot of idle time in the system, and we can kind of figure out a little bit where that could come from. Oh, I apologize here, right? So first of all, theoretically, we should only need 3.8 workstations, but then we rounded up to 4, and we ended up using 5, right? And why was that? Because of all this idle time right there. There's a lot of idle time right there. Particularly this dude over here, 41 seconds of idle time. That's crazy. So let's see if we can proceed with the same kind of process mapping that we had before and that we learned in the previous lecture, right? So how can we go about doing this? Well, now I have workstation. So this is workstation 1, 2, 3, 4, and 5. And the average processing time of that workstation is as follows. 45 seconds for workstation number 1. So I'm summing up. So 45 seconds, 50 seconds, then all these, and then all this, and then all these. So 45 seconds, 50 seconds, 47, 44, and 9. Okay, so all I did was sum up these times. 45 seconds, 50 seconds. Now I have 11 plus 15 plus 9 plus 12, right? So that is 47. Oh, where did I go? Sorry. Now 12 plus 12 plus 12 plus 8, that is 44. And then lastly, 9 seconds over here, 9 seconds over there. So I can think of that in terms of a capacity. So for me to look at capacity, remember that capacity is 1 over P, right? 1 over processing time. So a capacity in units per second would be very weird. So 1 over 45, that's 0.02. This guy is 0.02 something. This guy is 0.021 something. This other guy here is 0.0227. That's also really weird. And this guy is even less, 0.1111. That doesn't mean anything, units per second. So let's transform this into units per day. So I'm going to multiply all these guys by 7 hours. Each hour has 60 minutes, and each minute has 60 seconds, right? So in terms of capacity per day, station number, oh, and by the way, I apologize, I didn't mention the tasks. So station number 1 only has task A. Station number 2 has tasks D. Station number 3 has all these 4, right? Station number 4, this guy. Station number 5 is K. So you might want to ask, well, you know what, like you're showing here that station 1 goes after station 2. So theoretically, you could have something like this, right? 1 and 2, sure. But we're trying to get a linear flow to pass a point, right? So what is the capacity in terms of units per day? This guy, if I multiply this by 7 hours, by 60 minutes, by 60 seconds, I get 560 units per day. Remember, my demand is 500 units per day, right? So what do I get for station 2? This is 504. So pretty close to the demand. We know that already because there's not much idle time left. Remember those 50.4 seconds? There's only 0.4 seconds left for this guy. Let's see, what else? Station number 3. Station number 3 is 536.17. Station number 4 is 572.73. And station number 5 is a whopping 28,000. So 2,800 units. So we can figure out our utilization rate. How is it that we do that? We check what our demand is, and then we're going to divide our demand by our capacity, right? So let's see how that goes. In terms of utilization, station 1, I'm at 89.3%. So a little bit of extra capacity there. Station number 2, 500 divided by 504. So that's 99.2% utilization, which is really high. So far, this is the highest utilization, right? Station number 3, 93.3%. Station number 4, so the 500 units divided by 572, I get 87.3%. And then station number 5, 500 units a day divided by 2,800. This is 17.9% utilization. The bottleneck is always a single bottleneck, and that will be the one with the highest utilization. So that is very clear that the bottleneck is this guy over here, right? So here's my bottleneck right there. And we know that we had a hunch that this would be the bottleneck because there's so little idle time left, right? Okay, so what is the flow rate? The flow rate is the minimum between demand and capacity. So lo and behold, it would be the minimum between 500 and my capacity, right, which is 504. So my flow rate is 500 units per day. How does that sound? And what would be my cycle time? Well, if cycle time is 1 over flow rate, then my cycle time is 1 over 500. And what would that be? That would be 50.4 seconds. So how did we get to this number? Have we seen 50.4 seconds before? Does this mean anything? Is it a little bit circular, maybe? What would that be? So what is going on? Right? So my flow rate is exactly those 500 units per day, and the cycle time that we ideally would have would be those 50.4 seconds. Now, remember, this will be the theoretical cycle time. What is my actual cycle time? It will be this guy over here, right? So my flow rate, therefore, should be related to these things. All I'm showing you right now is that by looking into what the demand looked like, 500 units per day, I can then work my way backwards into my process, right? So 50 seconds. This is this would be my ideal cycle time. This is the closest I can get to balance my assembly line given the tech time or the demand that I had before. Okay, so with that being said, this is how you balance a more complex problem. And if you have any questions, as usual, you can contact me. So thank you all very much, and I hope you enjoyed this tutorial. How do I stop recording, stop sharing, and